Welcome to The Explainer. So today we're diving straight into a really incredible technological leap taking place in the world of life sciences and biomanufacturing. For decades, discovering a new vaccine, synthesizing a gene, or screening for natural products meant dealing with one massive, tedious hurdle, and that's picking microbial colonies. It's a process that has traditionally kept brilliant scientists tethered to lab benches, honestly acting more like manual laborers than actual innovators. But that is fundamentally changing. Today, we're looking at the massive shift from slow, traditional laboratory screening to massive, industrial-scale automated production. We're going to check out the hardware making this possible and see exactly how it's completely redefining the speed of biological discovery.
Okay, let's take a quick look at our roadmap. First up, we'll examine the bottleneck in traditional screening. Then, we'll get into the paradigm shift of the single-use sampling ball. Next, we've got an objective head-to-head comparison between the Q-Pix Flex and the OnePoo workstation. And finally, we'll explore large-scale production scenarios. Let's jump in.
Section 1. Breaking the bottleneck. The slowdown in science.
Think about this for a second. In fields like synthetic biology, protein engineering, or environmental microbiology, every single tiny colony sitting on a petri dish could hold the next massive breakthrough. But actually identifying and transferring those target colonies into a new culture medium, it's a massive pain point. When a lab needs to process hundreds or even thousands of samples, traditional manual labor simply breaks down. It's slow, it relies heavily on the operator's experience, and it's incredibly vulnerable to just plain old human fatigue. And, even traditional automated equipment has its limits. Which brings us to the fundamental question that's currently keeping lab managers and biotech execs up at night. How can we screen thousands of colonies continuously at massive scale without the risk of cross-contamination? Because it's not just about moving fast, right? It's about moving fast while maintaining absolute purity and traceability.
To really understand why this is so difficult, let's look at the traditional automated loop. Most automated pickers out there use reusable metal pins. So the machine picks the colony, sure, but before it can pick the next one, it has to go through this really rigid, time-consuming cycle. It has to wash the pen, sterilize it, usually with intense heat or UV, and then, crucially, it has to cool it down. Because if that metal pin is even slightly too hot, it'll instantly kill the next bacteria it touches. Plus, traditional pins actually pierce the agar, which can cause the culture medium to break and splatter, and that just leads to more contamination. Basically, this whole wash and cool cycle just creates massive downtime.
Moving on to Section 2, the paradigm shift, the OnePoo solution.
And that brings us to the OnePoo Automated Colony Sampling Workstation. Right off the bat, this is not your standard small benchtop instrument. It is a comprehensive workstation built to integrate everything from barcode scanning and smart imaging all the way to target picking and automatic capping. But here's the thing, the real magic isn't just in the sheer size of the machine, it's actually in a tiny proprietary piece of hardware it uses to do the physical sampling.
This is where the paradigm shift really happens. The single-use sampling ball. Instead of using a sharp metal pen that constantly needs cleaning, the OnePoo system uses a disposable sphere. It's basically like a microscopic golf ball. The source data points out that its uneven microtextured surface hugely increases its surface area, which makes it absolutely perfect for grabbing and holding onto bacteria. So the machine precisely moves this little ball over to the target colony, touches it, and then literally drops the entire ball, bacteria and all, straight into the target liquid medium. There's no retrieval, no washing, no sterilizing, no cooling downtime. The machine just instantly grabs a fresh ball and keeps right on going.
So what does this actually mean for performance? Well, based on over 100,000 internal tests, this drop-and-go method hits a 99.99% sampling success rate. And because the tool is literally never reused, the cross-contamination rate just plummets to under 0.0001%. It's literally eliminating the risk of cross-contamination right at the source, while completely wiping out the downtime that you'd normally get from those old cleaning cycles. It's a real game changer.
In 3, the showdown, Q-Pix Flex versus OnePoo.
Now, in the world of automated microbial screening, lab managers are usually comparing different solutions. Looking at these two side by side, the form factors tell you immediately that they operate on completely different philosophies. On the left, you've got the Q-Pix Flex. It's compact, highly integrated, weighs about 80 kilograms, and it's designed to fit perfectly right onto a standard lab bench. On the right, the OnePoo system is this massive industrial unit. It weighs significantly more, requires dedicated factory floor space, and needs higher power outputs. Let's dig into the hard data here. The Cupix Flex processes around 350 colonies per hour when using disposable pens. Meanwhile, the OneFu system maxes out at a staggering 6,000 units per hour. But throughput isn't the whole story here. You have to look at the target users. Cupix is built for lab R&D. It supports a huge variety of standard plates, from Petri dishes to complex 384 well plates, and you can easily swap between reusable and disposable pens. OneFu, however, is built exclusively for large-scale factory production, relying entirely on those single-use balls to maintain its ultra-fast rhythm.
So, to put that into perspective, these aren't exactly one-to-one competitors. They are highly specialized tools for very different jobs. Think of the Cupix Flex as your versatile multi-tool. It's got a 4-channel liquid handling system, it can plate, streak, and pick, and, this is a big one, its compact size means you can physically place it directly inside low-oxygen or anaerobic chambers, which is absolutely vital for certain types of biology. The OneFu, that's your heavy-duty industrial engine. You are not fitting that in an anaerobic chamber. But if your only goal is ultra-high throughput, continuous sampling of massive clone libraries, it's going to give you exactly that.
Section 4. Moving toward large-scale production. When we actually make the jump from the lab bench to the full biomanufacturing floor, the requirements change drastically. It's no longer just about picking a colony, it's about plugging that action into a massive, overarching digital pipeline. This is where the whole microfactory concept comes to life. Industrial workstations like the OneFu are built for 365-day, 24/7 continuous operation. But more than that, they act as massive data hubs. They use visual block-style programming, read barcodes and QR codes, and seamlessly link the exact origin of a source colony to its final destination. That data goes straight into enterprise systems like MES or ERP databases, or right up to the cloud. Plus, those 20-megapixel industrial cameras they use aren't just snapping photos. They're feeding live data into AI models to constantly get better at identifying colony shapes, colors, and even fluorescence. Your daily lab work literally becomes a permanent digital asset for the company. Which brings us right back to this crucial number, 6,000. When we say 6,000 units per hour in a production setting, the source data is very clear that this isn't just the mechanical speed of the robotic arm flapping around. It's the full process, real-world throughput. It includes the time to automatically load the material, scan the barcode, pop the lid, image the dish, run the AI recognition, pick the colony, drop it in the target plate, close the lid, and log all the data. The whole shebang. Achieving that speed end-to-end is what makes a genuine automated microfactory a reality.
And I think this quote perfectly captures the core philosophy driving this whole shift. Make every sampling more accurate, make every piece of data traceable. Why does that actually matter to us? Because in biomanufacturing, variability is the ultimate enemy. By handing these super repetitive, massively scaled tasks over to intelligent workstations, we're completely eliminating human error and fatigue. We standardize operations across every single shift. So, if a massive breakthrough happens on a Tuesday at 3 a.m., every single variable is perfectly tracked, verified, and completely repeatable.
Which leaves us with this final thought to chew on. We've seen exactly how this tech has evolved, from manual pipetting by hand to versatile benchtop robots like the Cupix, all the way to these massive AI-driven microfactories using single-use sampling balls to hit zero downtime production. So, as scientists are finally freed from the mind-numbing labor of manual picking, what hidden biological discoveries, new antibiotics, engineered proteins, sustainable biomaterials, what are we finally going to have the time, the energy, and the sheer scale to unlock? Thank you so much for joining me on this explainer, and I hope this deep dive into the hardware of synthetic biology gave you a solid look at where the entire industry is heading next. Catch you next time.